Hi, I'm Hein, and this week I'm gonna review about the multigate. As we mentioned before, when we scaling down the device, it has some problems like SCE. When we scaling the gate lengths, the electric field in the lateral directions become bigger, so it is hard to control the channel with controlling the gate bias, and we can also have the problems like punch through. To solve these problems, we have to change the structure of the device. For example, at first we use the SOI structure, the silicon on insulator. By blocking the fringing electric field of the source and drain with silicon dioxide, we can control the electric field that electric field overlap that occurs in the deep inside of the body. But it have some problems like self-heating or the increase of the series resistance because the channel is very small. So we have to change the other structure like the like using the multigate like FinFET or GAA structure. The FinFET is a structure have the gate tri-gate structure, so we can control the channel by in three directions: the top side and the both side. And the GAA is the gate all around the structure, so we can control the channel at the for all the directions of the channel. But when we scaling down the device, there are some problems in this structure because this kind of structure become the quantum mechanical structure. So in this situation, it is very important to consider some effects that can occur in the quantum mechanical situation. The first thing is controlling the thickness of the body in FinFET, the width of the fin, because it is very important to make the fully depleted channel in this structure, because when we make a fully depleted channel, the effective band gap can increase because the inner state is quantized, and when we increase the length of the channel, when we increase the length of the quantum well, the inner state quantization become more bigger, so we can think the energy band gap is become bigger than when the quantum well's width is big. So it means the increase of the effective band gap can thought as the increase of the threshold voltage in the device. So it is very important to think about it. And second, to make a fully depleted channel is important to control the subthreshold swing, because when we calculate the subthreshold swing, we can have to consider the ideal constant n, and the ideal constant n is relative to the capacitance of the body. But the body capacitance is dependent on the depletion charge of the body. So when we decrease the dependent charge of but when the fully depleted structure, when we have the fully depleted structure, it means the change of the depletion charge are 0, so the ideal constant can more close to the 1. So it means we can decrease the substructural swing. So to make a low fin width, to make a fin width have the low width is very important. But when we decrease the width of the fin, it is very hard to control the series resistance because the fin size is small, and the drain current because the fin size is also small. So we have to make the fin height more taller to increase the pin width, and the number of the pin, increase the number of the fin to increase the total width of the fin. And second thing we have to think about is the natural length. Natural length is the minimum distance that can endure the short channel effect. To scaling down the device constantly, we have to less the natural length, because to make a device which acts properly, we have the channel at minimum channel length and minimum, the channels have to equals the natural length times from 4 or 6. So it is very important to decrease the natural length. To decrease the natural length, we can use the method using high K material and ultra thin body. And the good method to decrease the natural length is using the multi-gate, because the number of the gate is dependent to the natural length. The second thing we have to consider when we make a quantum mechanical device is the volume inversion. The volume inversion is the situation which the carriers exist in the center of the channel when the device size is too small. In this case, the carriers are more free from the surface scattering, so we can increase the mobility of the device. But when we have the too short the channel lengths, although the carriers are in volume inversion state, but it is too close from the surface, so it can be affected by the channel scattering, the surface scattering. So we have to control that too. The last thing we have to control is inter-subband scattering. The inter-subband scattering is the situation when the carrier does not have the strong energy. It means it have enoughly low energy. They can't move the other state, so in the state they already exist, they are scatter each other. It means the inter-subband scattering. In this case, this situation can decrease the mobility, so we have to think about that effect when we make a device. In the past, when we use the bark structure, the inter-subband scattering does not exist, but when we use the quantum mechanical structure like FinFET and GAA nanowire, we can find the inter-subband scattering at the cryo temperature. But nowadays the device size is too small, so we can have to